In this video, we present the lucidtouch, a see-through mobile device. See-through mobile devices allow users to see their hands while working behind the display. In what we have termed pseudo-transparency, the hands are shown, but other objects behind the device are not. Many mobile devices use touchscreens calibrated for direct touch input. Although intuitive, direct touch input suffers from imprecise selection, due to occlusion and the arbitrary mapping of touch area to cursor position. The lucidtouch overcomes this problem by allowing touches from behind the device. By holding the lucidtouch between the palms of the hands, users are able to comfortably give touch input from all of the fingers located behind the display. A passive touchscreen on the front of the device allows for conventional direct touch input with the thumbs. The lucidtouch prototype uses a camera pointing at the back of the display to capture the position of the hands. Future implementations of such devices would likely include alternative sensors embedded in the body of the device. Once fingers begin to touch the back of the device, the tracking of their positions is handled by a FingerWorks eye gesture pad mounted behind the display. The lucidtouch is limited by presently available technology. This sketch illustrates the form factor future implementations might employ. Despite these limitations, we are able to use the current implementation to begin to explore interaction with a see-through device. Pseudo-transparency is augmented by vision-track touch cursors. While it is possible to visualize the touch cursors without overlaying the image of the hands, this makes it difficult for the user to associate each touch point with a particular finger. While hovering, touch cursors are red. When the finger makes contact with the back of the display, the touch cursor turns blue. Having established the look and feel of the pseudo-transparency in cursors, we are able to explore interaction designs. We first examined the issue of dragging. Although a user can reach across the screen while holding the device in the other hand, it is cumbersome to change postures. Instead, the user might decide to hand off the object between the hands. To ease this handoff, we implemented a special drag technique. As objects are dragged towards the center of the display, they expand to ease selection with the other hand. Next, we examined text entry. A traditional soft keyboard can be used with 2 touch points. Because this does not leverage the other fingers, however, input is slow. To utilize additional fingers, we modified the keyboard so that the relative positions of the keys and fingers would be maintained for touch typists. This layout allows more fingers to reach the keys while leveraging previous learning. Finally, we turned our attention to implementing a classic of multi-touch input, the map browser. As the map is touched with 1 or 2 points of contact, it translates, rotates, and scales as necessary to maintain its position on those touch points. Unlike traditional direct touch input, no portion of the map is occluded while browsing. In this video, we have demonstrated pseudo-transparency for occlusion-free direct touch input and the lucidtouch, our multi-touch see-through device. By providing techniques for cursors, pointing, dragging, text entry, and classic multi-touch interaction, we believe we have demonstrated a solid foundation for the future development of compelling mobile devices.